A new narrative is emerging in the world of capital. The rise of custom AI ASIC chips could challenge the dominance of general-purpose GPUs in the AI market. Recently, Morgan Stanley published a report titled AI ASIC 2.0 Potential Winners, suggesting that ASIC chips with their optimized performance and cost advantages may gradually capture more market share from NVIDIA's GPUs. The report predicts that the AI ASIC market will grow from $12 billion in 2024 to $30 billion by 2027, with a compound annual growth rate of 34%. For those familiar with our previous videos, you might already have some understanding of ASICs. An ASIC is an integrated circuit designed and optimized for a specific application. Unlike general-purpose processors such as CPUs or GPUs, ASIC hardware architectures are entirely tailored to perform a specific task. You can find ASICs commonly used in areas like 5G communication, AI inference, cryptocurrency mining, and audio-video processing. This specificity explains the advantages and disadvantages of ASICs compared to GPUs. For example, advantages of ASICs. That is high performance for specific tasks, lower power consumption, and cost efficiency. And disadvantages of ASICs. That is fixed functionality. Once produced, ASICs cannot be modified or upgraded through software. Limited flexibility. Their application scope is restricted to specific tasks. The story of chips begins in 1958. Back then, electronic devices were large and complex, requiring many circuit boards and connections. It was during this period that Jack Kilby, an American engineer working at Texas Instruments, designed a silicon chip containing a single transistor. At the time, the idea of integrating circuits was not widely accepted, as many believed it would cause signal interference, overheating, and other problems. However, Kilby successfully demonstrated its feasibility. By 1965, Fairchild Semiconductor could integrate 50 transistors onto a single silicon chip. In the same year, one of Fairchild's founders, Gordon Moore, observed this trend and proposed the now famous Moore's Law, which predicted the doubling of transistor density approximately every 2 years. In 1971, Intel introduced the world's first microprocessor, the 4004, which integrated CPU functionality onto a single chip. In 1999, NVIDIA launched the GeForce 256, the first GPU capable of performing complete graphics processing tasks. Fast forward to 2023. Apple released the iPhone 15 Pro powered by the A17 Bionic chip, boasting 19 billion transistors. From Kilby's single transistor chip in 1958 to today, transistor density has doubled 34 times over 56 years, transforming computing power and affordability to levels that made handheld devices like smartphones ubiquitous. Just as Moore's Law appears to be slowing, the rise of AI, particularly large language models, has accelerated demand for advanced chips. AI neural networks require extensive training to develop effective models. Training involves vast amounts of data, with neural networks adjusting millions or even billions of parameters, weights, and biases to minimize prediction errors. This massive computational demand necessitates highly capable chips. While AI training imposes substantial requirements on computing power, it's not the only application with such demands. The gaming industry's need for realistic video rendering drove the creation of GPUs 25 years ago. NVIDIA designed GPUs to meet these massive computational requirements, which explains their seamless application in AI tasks today. GPUs allow for processing large datasets in parallel while consuming relatively less energy. The advent of AI models like OpenAI's ChatGPT has further increased the demand for computing power. In 2018, Alec Redford, a researcher at OpenAI, developed the first generative pre-trained transformer, GPT, leveraging the transformer model architecture introduced by Google researchers the year before. Training GPT-4, for instance, required 25,000 NVIDIA A100 GPUs, clustered to minimize time and energy losses during data transfer between chips. However, GPUs have limitations in specialized applications. Their general-purpose nature leads to inefficiencies, high energy consumption, and high costs. This has spurred the development of ASICs designed specifically for AI training and inference tasks. Currently, ASICs for AI inference are more mature and widely adopted than those for training. Will the rise of ASICs threaten NVIDIA's dominance in the chip market? The answer, at least in the short term, is no. NVIDIA's GPUs have a key advantage: flexibility. Through platforms like CUDA, NVIDIA supports software adaptation to different workloads, making GPUs highly versatile. CUDA has essentially become an industry standard, playing a decisive role in connecting networked chips. This level of flexibility is something ASICs cannot currently match. Morgan Stanley's report also points out that the rise of ASICs does not signal the decline of GPUs. Instead, the two technologies are expected to coexist for the long time, each catering to different use cases. The rising value of cutting-edge chips has turned them into a geopolitical tool. Although the chip industry appears globalized, key technologies are controlled by a few countries and companies. For example, NVIDIA designs its chips in the US. ASML in the Netherlands manufactures the lithography machines essential for etching circuits onto silicon wafers, particularly for advanced processes. Only TSMC in Taiwan and Samsung in South Korea can currently mass-produce chips smaller than 5 nm. Japan produces critical materials like photoresists for lithography and silicon wafers. These key technologies have become focal points in the strategic competition between the US and China, with chips playing a crucial role in shaping technological and national strategies. Chips, despite their small size, played an outsized role in technological and geopolitical developments. The evolution of this industry continues to reshape our world, and the competition among chips, whether GPUs or ASICs, will define the next chapter in computing innovation. For now, we can only watch and wait to see what unfolds. Okay, thanks for your watching today. See you next time.